Hello, my name is Omid Salehzadeh. I am working with Professor Simon Watkins at Simon Fraser University. Today, I will be talking about geometric limits of coherent 3-5 radial heterostructure nanowires. So as you know, nanowires are being used in many nanoscale devices such as LEDs, transistors, solar cells. In solar cells, this geometry of nanowires enhances the light trapping due to multiple reflection from sidewalls, which make the light absorption more efficient. So here I'm showing two examples of solar cell nanowires, gallium arsenide based with efficiency of 6.6%, which was published just 2 months ago, and this one indium phosphide based with efficiency of 13.8%. So to grow this structure, there are several challenges. The first important one is the doping of this structure to make reliable and abrupt p-n junctions. And the next one is to passivate the surface of this nanowires to avoid the surface recombination. So this is usually been achieved by growing a shell with a wider band gap around the core. So sometimes this shell has some lattice mismatch with the core, and if we are above the critical shell thickness, dislocation will be formed at the interface, which will degrade the device performance. Therefore, we need to be aware of these geometric limits of coherent core shell nanowires. So in the case of thin films, if the layer is thin enough, all the strain will be accommodated by the layer, and the layer will be lattice matched to substrate. And if the thickness is higher than a certain value, the dislocation will appear right at the interface. So in the case of core shell nanowires, we consider coaxial cylinder in cylindrical coordinate system. In this case, since the core is thin, the core atoms also can accommodate part of the strain, which makes the critical shell thickness larger for these structures. So our goal here is to determine the strain components and total strain energy, which we will do this numerically. Then easily we can determine dislocation energy in two different structures. For Wurtzite we can use this, and for zinc blende we can use this. Then easily by comparing strain energy and dislocation energy, we can estimate the critical shell thickness. So to determine this strain components, we have to look at these displacement vectors, which are the actual displacement of these atoms. Then after we find that, we can find strain components, then we can find total strain energy. So to find this U vector, we use equilibrium equations of elasticity, which has these simple solutions with 8 coefficients. So we need to apply appropriate boundary conditions to determine this coefficients. So first, this in radial direction, U has to be finite right at the core, which gives us this to be 0. This one is 0 due to the axial symmetry. Then the lattice constant has to be same in axial and tangential direction right at the interface to maintain the coherency. It gives us this constraint here. Then the stress normal drift to the free surface has to be 0, which gives us this boundary condition. Then we need two more boundary conditions. We set this interfacial strain in axial and tangential direction to some parameters, and we will try to find these values such that to minimize the total strain energy. So having this 8 boundary condition, we can find expressions for this. Then we can find expression for total strain energy, which is a function of core radius, shell thickness, and these two parameters. Then we can minimize the total strain energy with respect to these two parameters to determine the total strain energy and strain components. So this graph shows some numerical result. This is strain, and this is radial position from the center of the core to the shell. Core radius is 20 nanometer and shell thickness is 10 nanometer. So the structure is indium arsenide core, indium phosphide shell with Wurtzite structure. So for indium arsenide core, we can see the strain is negative, meaning that it's under compressive strain. And in the shell, in the axial and tangential direction, it's positive, meaning that it's under tensile strain, while in the radial direction it's compressed because we have a free surface here. So if we stretch in two directions, since we have free surface, it will shrink. So one important thing here is that this tangential strain is position dependent. It just rapidly drops toward the surface. So we did similar calculation for indium phosphide, indium arsenide core shell, which we see exactly opposite sign for the strain. Then we did this type of analysis here. This is strain components versus shell thickness for a core radius of 20 nanometer. We see that when this one shows the strain component in shell, this one for core. We see if we increase the shell thickness, the axial strain decreases in the shell and it transfers to the core. However, this tangential strain is always accommodated by the shell, no matter what the thickness of the shell. This is very important and easily can be understood from this fact here. So tangential strain is constant in the core, but it decreases in the shell toward the outer surface. So therefore, energetically, it's more favorable for the shell to accommodate the strain because it will decrease rapidly, and therefore the total strain energy will be small. But in the axial case, the strain energy is constant for both of them. Therefore, the axial strain has to be distributed in the core and shell such that to minimize the total strain energy again. So this one shows the energy of total strain energy and dislocation energy. So this is dislocation energy, and strain energy increases with shell thickness. At some point, it exceeds the dislocation energy. This point is the point that we lose our coherency and dislocation will be formed. So we did similar analysis. We kept the shell thickness constant. We increased the core radius. Again, the tangential strain is accommodated by the shell, and increasing core radius, axial strain in the core decreases and the shell increases. So for the dislocation energy increases linearly with core radius, and strain energy also increases. At some point, it exceeds the dislocation energy, and at that point, we will have dislocation. So doing those type of calculations, we can make this type of graphs, critical shell thickness and core radius. Each of these graphs correspond to this structure with different lattice mismatch. Below this curves, the structure is coherent, and above that one we have dislocation. So we can see decrease in the core radius, critical shell thickness increases, and after some value for the core radius, the critical shell thickness tends to infinity. So I summarize this here. This one, the critical core radius, increase in lattice mismatch, critical core radius, this value here decreases. Also, critical shell thickness at this part, which is constant, it decreases with increasing lattice mismatch. So here I'm showing some experimental results. This is Wurtzite, indium arsenide, indium phosphide core shell structure. Here the core radius is 17 nanometer, shell thickness is 20 nanometer. The structure is coherent. We don't see any dislocation here. But for a thicker core radius of 30 nanometer above, we see these dislocations here and here. So you can see the contrast exactly stops right at the interface. It's not just dislocation loops around the core. Also, I'm showing this one here. This structure is coherent, but we have some stacking faults. The difference between stacking faults and this dislocation is that this one stops right at the interface. This goes all the way to our outer surface. And here is more experimental result consistent with our predictions. We can see for a core radius of 10 nanometer, we can grow shell thickness of 35 nanometer, which is 8 times higher than the value reported for thin films. Also, we work on zinc plate, gallium arsenide, gallium phosphide, and gallium arsenide, gallium antimonide structures. This one has very large lattice mismatch. So in this case, we see if the shell thickness about 10 nanometer, we are going to have this dislocation. We have some extra planes right here. The line direction is toward the page, and the Berger's vector is along the nanowire. So also here we see this dislocations. You can see some extra planes here. And if you want to grow a coherent structure, the shell thickness in this case has to be below 2 nanometer, which we have grown such structures. So in summary, I presented some numerical calculation which shows that strain distributes both in core and shell. Core takes mostly the axial strain, and the shell takes mostly the tangential strain. Then we presented some experimental results consistent with our calculations. Also, the fact that axial strain is dominant in core and tangential strain is dominant in shell tells us this dislocations usually will be formed in a configuration that the line direction is perpendicular to the nanowire axis. In this case, axial strain, we can easily relieve the axial strain, lowering the total strain energy. Thank you.